Okay, let's get started. Welcome everyone to the April meeting of the Royal Astronomical Society of Canada, Ottawa Centre. We've got a great program for you tonight. As usual, we'll have Dave Chisholm give us our Ottawa Skies update. Al Scott will be giving us our 10-minute astronomy news update. Michael Wolfson has returned to give us the second half of his presentation on his trip to South Africa. And in the second half, we've got a special guest from Carleton University, Dr. Andrea Lobel, to give us a presentation on Mesopotamian astronomy. So here are our new members. Let's give them a warm welcome. We've had 14 new members thus far in 2018. Thanks all for joining. All right, so let me hand the podium over to Dave Chisholm. There you go.
The one on the right? Okay.
The one on the right.
Okay. So good evening, folks. So let's take a look at the moon phases for April. So we've got our full moon on April the 30th. We do have some meteor showers this month. The largest meteor shower, April 22nd and 23rd. And it peaks that night. And after midnight, the moon will have set, and that would probably be the best time to observe them. And we're looking at about 20 meteors per hour for this particular meteor shower. Mercury, best time to attempt to observe Mercury is on April 29th, where it reaches its greatest western elongation. That means it's the furthest away from the sun. It's 27 degrees away. You might be able to spot it low in the eastern sky just before sunrise. Venus is visible all month after sunset, and Mars is visible in the early morning. Jupiter is visible all night. Saturn is visible in the early morning all month, and as you can see towards the end of the month, what you're seeing there are the rise and set times. Starting probably next month, middle of next month, we'll start to be able to see Saturn at a decent time. Uranus is visible in the early evening, first half of the month, and Neptune is not visible. International Space Station, best viewing date is April the 8th. It rises up to 74 degrees, and magnitude is about 3.8. There's how it's going across the sky. Next month, I'm going to take you how I go do these particular calculations and how to look them up. The problem I have is that the predictions are only good 10 days in advance, so I can only give you the best observation in the next 10 days. So next month, my presentation will explain in more detail how you do that. And there's my cartoon of the month. Thank you.
Thanks, Dave. All right, next we've got Al Scott with the 10-minute astronomy news update.
Thank you. So I've got a couple interesting news items for you this month. First one, it's a discovery. Whoa. Went backwards. Discovery of a new galaxy, and here's a picture of the galaxy on the right, and the instrument that was used to discover it on the left is called this is the Dragonfly Eye Array. It's an array of basically Canon telephoto lenses with very low reflectivity. It's able to detect because it's got low reflectivity on the lenses, they're specially made, it's able to detect very dim items. So this galaxy really looks more like a smudge than a galaxy at first glance. And it was discovered based on a few bright dots that turns out to be globular clusters. And when looked at with the Dragonfly Eye, you could actually find that it actually is a relatively large galaxy. It's called Ngc 1052-DF2 for Dragonfly Eye 2. And this galaxy is unique in that it appears to have no dark matter. Thus the name that I coined. Astronomers have found that this diffuse galaxy has at most 1/400th as much dark matter as expected, based on other galaxies of similar mass, based on the brightness of the stars. It's one of a collection of galaxies dominated by the large elliptical Ngc 1052, which lies about 65 million light years away on the border of the constellations Cetus and Eridanus.
Which one is it, Al?
It's this entire area.
Oh, the whole area.
Yeah, it's a big fluffy foreground galaxy. The surface brightness is so dim that it's difficult. It hasn't been detected before using normal telescopes. It just looks like a smudge.
What's the field of view?
I'm not sure. I'd have to look that up. The galaxy is so sparse that it's see-through, and its dots look like globular clusters, albeit strangely bright, similar to the Milky Way's Omega Centauri cluster. Those globulars are, based on the distance, they're about twice as large and squashed as globulars of similar brightness in our galaxy. But maybe this is because they don't have dark matter. These ancient globulars loop around the parent galaxies with speeds determined by the galaxy's mass. And you can measure the Doppler shift of the emission lines from these globulars and thus get a measurement of how much mass is in the galaxy by how fast the globulars are going around at their particular radii. The 10 globulars the team clocked all move at most a third as fast as expected for galaxies of this mass, of about 200 million suns, about a tenth the size of the Small Magellanic Cloud. So that means that the enclosed mass is roughly equivalent to the visible stars, which is somewhat unique because all other galaxies that have been measured up till now have an extra oomph in them that make their globulars go faster than you might expect from the visible stars. So the ironic part about this discovery is that if confirmed, it ironically verifies the existence of dark matter as a thing that can be missing from some galaxies and not as a problem in our understanding of gravity at large scales, which some other people have theorized, and I've talked about that before. So it's an interesting discovery, and if it's confirmed, it's very important in the search for dark matter. And they're looking at a few other different candidates with this array, so stay tuned for more discovery announcements, hopefully. This is another interesting experiment. Does anybody know what this is?
Shiny table
Yes.
in the middle of nowhere.
It's a radio telescope. Exactly, in the Australian outback. So, after the early universe cooled, most of the matter existed in the form of extremely dark clouds of neutral hydrogen. There were no stars immediately after the Big Bang as the universe cooled. It was basically just molecular hydrogen that was cooling and cooling and cooling, basically only warmed by the cosmic background radiation. And for years, astronomers have been trying to detect this neutral hydrogen via its telltale 21 centimeter radio emission line. In particular, they want to see how the energetic radiation from the very first stars and galaxies heated and ionized the surrounding neutral gas. And this is what's called the Epoch of Reionization, when the neutral gas is reionized by the ultraviolet light from the first stars. And this tells us something about when these first stars formed in the history of our universe. Now, we believe that this is somewhere between 300 and 500 million years after the Big Bang. And as the radio waves from this 21 centimeter hydrogen emission line expand through space, they become meters long and become redshifted into the hundreds of megahertz range. And so what this is basically a radio telescope looking in that spectral range for these emission lines from neutral hydrogen. Unfortunately, the signal is swamped by man-made foreground sources, by electrons spiraling around magnetic fields in our own galaxy, and instrumental noise. So this particular experiment is called EDGES, Experiment to Detect the Global Epoch of Reionization Signature. And this is a relatively cheap experiment, as you can see. And they put it out here to get it away from radio noise, basically. So they've detected a signal between 50 and 100 megahertz, which corresponds to a look-back time on the order of 180 million years after the Big Bang. At that very early stage in cosmic evolution, the cosmic background radiation would actually have been hotter than the neutral hydrogen gas, which is decoupled because it's transparent to the wavelengths that would be emitted by the 50 degree Kelvin background. So it's like you're surrounded by an oven at 50K, but the clouds are cooling even further because the oven isn't heating them up. The energy from the cosmic microwave just goes straight through these clouds without heating it up. And this 21 centimeter emission line goes straight through the universe to us. That's why they pick it out, because it's a highly forbidden line and doesn't interact with very much before it gets to us. So what they found was that this hydrogen gas actually, when it's hit by the ultraviolet rays of the first stars, it disturbs the electron and takes this gas out of equilibrium with the background radiation, and it allows it to either emit a signal on top of the background or absorb a signal below it. So when the ultraviolet radiation first hits this stuff, it knocks it out of equilibrium. We should be able to detect either a peak or a dip in the spectrum. And what these astronomers have found is a dip in the spectrum around 78 megahertz. And that's a wavelength of 3.84 meters. So this detection is basically the first measurement of this neutral hydrogen gas and the first measurement of the epoch of reionization. When were the first stars beginning to form and beginning to reionize the gas? And it took the team 12 years to tease this signal out of the data, of taking data, averaging the radio back. They're basically measuring radio hiss and trying to get rid of all the foreground sources and try to understand their instrument. So 12 years of measurements and then 2 years to rule out any systematic effects in their instrument before they could publish their data. And it's interesting data. Basically what it says is that the temperature of the hydrogen gas is only about 3 Kelvin. And predictions had said it should be about 7 Kelvin based on cooling from the Big Bang. So it's colder than expected. The dip is deeper in this radio spectrum than they otherwise would have expected. And so what they're proposing is that this gas is being cooled by interactions with the dark matter, cooled beyond what otherwise would have been predicted by normal theory. And it also then tells us a little bit about what the dark matter is. It's able to interact at a certain rate with the neutral hydrogen gas to cool it over hundreds of millions of years by a couple degrees. So a very interesting result from what seems to be a very humble experiment.
Yeah, can I ask a question?
Yes?
Is the map that's around it, it looks like some sort of wire, is that part of the radio telescope as well?
Yeah, I think that's a ground plane.
The ground plane?
Yeah. And there's an instrumentation shed off to the side.
So it's not a very large aperture way. Is this tabletop?
Yeah.
Wow.
Yeah.
What's the scale of this table?
It's like a table. You could walk up and have lunch on it. And because it's a small aperture, it obviously has a large field of view, but they don't care because they're just integrating over the whole sky. So.
If dark matter can cool hydrogen, does that mean dark matter interacts more than just gravitationally?
I believe so.
Do we need electromagnetic interaction to cool anything or heat anything up?
Yeah, I'm not sure about the theoretical implications of the discovery, but you're probably right. You probably need some sort of electromagnetic interaction or some higher order interaction that we're not aware of. It does require some modification of our understanding of dark matter, if it's correct. The other option is that the cosmic microwave background was hotter at that time than predicted, but that seems less likely from initial theories. So, a very interesting result. So next, I'd just like to put up a slide recognizing Stephen Hawking, who passed on March 14th. As most of you are aware, Professor Stephen Hawking was a man who transcended boundaries. He not only showed us that one could survive a crippling disease, but it is possible also to capture the hearts and minds of the world while making major contributions to science and astronomy. His academic career introduced the world to a new way of thinking about the physics of black holes. In fact, most of his work was in thought experiments, in understanding the implications of our physical theories and pushing them to their extreme limits where other people had not been able to go. He was the first person to realize that the expanding universe, if you play it backwards to the beginning of time, required the existence of a singularity, as one might expect in the middle of a black hole, where all of the matter was condensed into one point. And that was one of his earlier contributions in his PhD thesis. He introduced the idea, a revolutionary at the time, that black holes will emit radiation. Black holes up to this point had been thought of as having an event horizon whereby once something passes in, it can never come out. And that's what the definition of the event horizon is. Not even light can escape from this sphere in space because of the intense gravity within it. But what Hawking realized was that quantum mechanics had not been considered in this explanation. And when you take quantum mechanics and meld it into relativity, what you have, quantum mechanics describes the vacuum of space not as a dead place, but as a frothing sea of virtual particle-antiparticle pairs that pop into existence for an infinitesimal amount of time and then disappear by annihilating just as quickly. And as long as they're antiparticle-particle pairs, their total energy is zero, and they disappear on a time scale within the Heisenberg uncertainty principle. That means that they didn't really exist. But if you place this frothing sea of virtual particle-antiparticle pairs near the event horizon of a black hole, where there's a huge gravitational gradient, that the immense gravitational tides would tend to pull these particle pairs apart. And one of them could spiral into the black hole and the other one could escape. And it would be like the black hole would be absorbing a negative energy particle and emitting a positive energy particle, and effectively it would look like the black hole was emitting radiation. So black holes, from this understanding, actually act like black bodies with a certain temperature which depends only on their mass. And over time, if there's nothing going into a black hole, all black holes will eventually radiate away all of their mass and disappear. But what he also found was that, or what has been found since then, is that black holes are really, really cold. In fact, you have to have a black hole as small as the mass of a moon, about 133 microns across, before it's warm enough to outradiate the cosmic background radiation. So anything bigger than that would actually be absorbing more energy from the cosmic microwave radiation than it would be emitting. So it would actually still grow. But very tiny microscopic black holes could evaporate over time. In fact, so the smaller black holes are hotter because they emit more particles, because they have less gravity. And they would tend to dissipate, and you may see these flashes of energy as these tiny microscopic black holes, if they did exist, would evaporate by Hawking radiation. This hasn't been observed yet, but it's an intriguing speculation based on bringing two diverse theories together. And Hawking is the one that brought this Hawking radiation to the masses. So I just want to end with a quote from Stephen Hawking. "I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there's always something you can do and succeed at. It matters that you don't just give up." Thank you.
Thank you, Al. Stephen Hawking will certainly be missed. All right, Michael, you're up next. You can advance the slides with the right. There's a green button for a pointer if you need it.
Okay. Ooh, bright lights. Good evening, everybody, and appreciate the opportunity to tell you part two of the story of my trip to South Africa. Some travelogue, then basically photographs from both the South African Large Telescope and then the Royal Observatory. Cape Town is in the lower left there. And you see on the map where Sutherland is. Let me also point out Pretoria, because I'm going to refer to it quite a bit later. The star party that I talked about in February was there. One of the signs along the way toward Sutherland, watch out for baboons and leopards. This is a panoramic view. It's about 10 or 15 kilometers, I think, heading northeast from Cape Town and looking back towards the Cape Town area. So I think Cape Town's somewhere over there. This is almost all the way to Sutherland, the town where the observatory is. And as you can see, it's a high, dry, desert-like area. I couldn't believe it when I saw this thing. I confess I haven't Googled it to see what it really is, but they claim there's a spaceport there that's on the road nearby. So the Southern African Large Telescope is the largest optical telescope in the southern hemisphere, but it's not an original design. It's based on something called the Hobby Eberly telescope in West Texas that was completed, I don't know, 5 or 10 years earlier. It is very large. It's got an 11 by 10 meter mirror. It's spherical, not parabolic, and it's composed of a bunch of segments, 91 in fact, and they're hexagons, and they're about 1 meter. They fit in a 1 meter circle, and each one is controlled by a series of actuators. All of these actuators are computer controlled, and I can't remember, but it's down to like tens of nanometers that these actuators can position the mirror in order to make sure that all 91 of them are pointing in the same direction. The other thing that's really unique and allowed the telescope to be built at much lower cost than usual is it can rotate in azimuth, but it can't go up and down. So this allows huge savings in the mechanical and structural cost of holding the mirror. It means that the telescope can't see at the horizon and it can't see at the zenith, but it can see a wide swath. Apparently 80% of the sky goes by what it can see. So if the mirror is only rotating, how the heck do you track something as the Earth rotates? Well, I'll show some slides in a second, but basically there's a gantry or girder structure up at the top, and the part that receives the optical focus, spectroscopes and things, moves around up there. And the main use of this telescope is spectroscopy. There's a picture of the overall plan, and you can see there's many telescopes here. This is the big one, the South African Large Telescope. And once the government had decided on this site and provided the infrastructure, a number of other telescopes moved there and established there. And so there, I visited quite a few of these. I'm only going to show pictures for a couple of others. But they are from the US, Russia, Germany, many countries. Some universities have their own telescopes there. This is connected, but the technicians and operators live in that building or work in that building, but there's a fiber optic cable that goes down to Cape Town where the researchers do most of their work. Just to know that we're in the southern hemisphere, here's a nice photo, and so those are the large and small Magellanic clouds. There's a museum I'll talk about in a few minutes, but these are two photos of a model of the large telescope, and you can see all the little hexagons in there. And this is the gantry or girder structure up at the top, which holds the spectroscope and other things, the end of one end of the fiber optic cable. And it just rotates around in azimuth. It doesn't go up and down. Now this is the best picture I could find. So this is the actual gantry at the top, and you can see the pod where all the equipment is. And I tried to blow it up before the pixels got too big. So there's a somewhat bigger image. Now, according to some of what I was reading, there are 6 motors that control the orientation of this thing, and there's X, Y, Z, and then there's some gimbals that keep it pointed in the right part of the telescope, and finally I'm guessing the sixth motor must be for derotation of the image if it's tracking something over time. This is a picture I took when I was there, and you see there it looks like a hole there. What they can do, these mirrors need to be recoded every year or so, and the nice thing about having a segmented mirror is you can take out one segment at a time, take it off and recode it, and it doesn't unduly impair the utility or usefulness of the overall telescope. That looks scary to me. This guy, I don't know what he has in his hand, but I hope it's tied on. Now, if you're wondering, this thing here is a tower, and there's a laser up here. And I don't know if they do it every night or once a week, but basically the laser shines down at the mirror inside, and it is used to collimate each and every segment. This kind of telescope just would not have been possible before powerful computers, because you've got, on the one hand, all the computers that are controlling each and every one of those 91 mirror segments, and you've also got computers that are continuously controlling the 6 motors that handle the orientation of the optical pod at the top. When we were there, these guys were looking at the base where it rotates. It rotates on air pucks, and somehow it seemed to have gotten stuck. And here they are again working around. So this gives you a better sense of the scale of the overall telescope. And that's the control room. Pretty empty, lots of computer screens, pretty boring, I think, unless you're observing. Now onto another telescope. This is something called the Grub Parsons telescope. It was in Pretoria in 1948 until 1974, and then was moved to the Sutherland site. And I think I'm not sure it was this one, it was one of the largest telescopes, if not for quite a while, for a couple decades in the southern hemisphere. So this, if you blow it up, is this. So I was quite impressed to see that for some people who have deep pockets and not so deep pockets and buy amateur astronomy gear, this is the same Bader Planetarium. And now there were a number of these kinds of things which are all sky instruments. This particular set is for geophysical observation. And the fellow who was taking me around said, and this is the reference to Pretoria, these things are so sensitive they can detect lightning over in Pretoria. So like that's hundreds of kilometers away. And that's a peek inside this white box with the instrumentation inside. Al just showed something called, I forget the name of the telescope, with the Wasp's eye or something like that. Dragonfly. So this is the WASP, wide angle search for planets, and it looks like it has the same Nikon camera lenses and CCD cameras at the back. Apparently there are 4 of these scattered around the planet, so they're continuously searching for planets in particular parts of the sky. This was an innocuous looking little telescope hut, and lo and behold, a Meade Schmidt-Cassegrain inside. And I don't know if folks have heard of APM, another pretty well-known maker of amateur telescope gear. So they made this 1 meter telescope. I'm not sure which university or whatever paid for it and located it there. It's remotely controlled. And the one neat thing about it is there's the secondary, and it shoots light back down through the hole in the primary, but there's a 45-degree mirror here, so the light comes out this way. So no matter where it's pointing, this is relatively fixed. So from the Sutherland out in the desert, I drove back down to Cape Town, and in a suburb of Cape Town, there's something called the South African Royal Astronomical Observatory, or Royal Observatory. Nowadays, it's both a historical site and a research center, connected, as I said, by fiber optic cable. The fellow who was taking me around at Sutherland said they have a problem with vandalism with fiber optic cable because I guess the vandals think it's full of copper. They don't realize it's glass. so they have to reinstall it every once in a while, repair it. This observatory, or this site, is famous for something called the Mclean Observatory, which has something called the Victoria Telescope. It's actually 3 telescopes. There's a number of other historical telescopes, plus archives and a small museum. The site was founded by the British Navy back in 1820, and part of the raison d'etre was to keep time, which is important for ships to be able to align their clocks so they can tell longitude. And in terms of the personnel back and forth, the history suggests or shows that it had close ties to the Greenwich Observatory in England. So when you walk into the main observatory building, this is what one sees in terms of the old library. There's sort of 19th century astrophysics journals there, and the person who was just a wonderful host for me there, Auki, part of his activity as a volunteer is working in the archives and cataloging things. And one of the things he showed me is this little notebook from 1882, and I'm not sure how visible it is, but that's a sketch of a comet that was discovered there at that time. And this is sort of the shelves, which are just full of things that are actually quite poorly documented or inventoried. So that's one of the things that Auki's doing. Here's a picture of Auki, and this is the Mclean Telescope or Observatory. And inside there are 3 separate telescopes, a photographic refractor 24-inch diameter, and 2 others. Interestingly, they all have the same focal length, and for the first 25 years or so, the main telescope was used primarily as a spectrograph. And after that, they would basically take pictures of the same part of the sky at 6-month intervals. So from the diameter of the Earth's orbit around the sun, they would get enough parallax to be able to estimate the distance to those stars. The thing that is so cool about this telescope, I've actually visited it twice. First time, I was blown away. We'll see in a minute. The floor, and normally when you have a refractor like we used to have outside the S&T, the Science Museum, is you need a big tall ladder if you're looking closer to the horizon. In this one, the whole wooden floor around the telescope is able to rise and raise and lower. And this is the hydraulic pump, and this is the electric motor, and this is the building that housed all the batteries to run this motor. Old lead acid batteries, more than 100 years ago. So here's a picture, 3 different pictures of the inside. So this is an old picture showing when the telescope was being built. Notice the fellow inside. This is the telescope today, and this is Auki sitting near the controls of the telescope. And the way spectroscopy was done, they didn't have, at least early on, diffraction gratings. They certainly didn't have digital cameras. So this is a huge prism. So it's flat on both sides, piece of glass, but the 2 sides are at different angles, so that it will create a spectrum. Now it's folded open here, but when you're doing spectroscopy, it's folded closed, and then at the other end, the astronomer doing the work takes pictures. And here you can see the front of the smallest, the I think it's 8-inch, and then the 18-inch here, and this is 24 inches in diameter. So that's how spectroscopy was done. And I think one of the claims to fame here was that with this they were able to discover oxygen in the atmosphere of some stars. Now the way they did it is they take these pictures and then they would use another spectroscope with a Bunsen burner or something, sort of a little one on a tabletop, and get the spectrum of things that we know about on Earth. And they would use these microscopes, and they put the film here or along here, or as this fellow's doing. In this case, I think he was doing the parallax calculations. Compare in order to figure out. And there's kind of a micrometer adjustment. Can't see it on this one right here on the edge. So you can slide this microscope back and forth. And that's the way they measured spectra. So folks doing it today with digital cameras have it easy. That's an old picture of the main museum room, and this is where they did the spectroscopy of earthbound substances in order to have comparators for what they were, the spectra they were seeing through the telescope. Now, folks over the years here at the RASC meetings, a couple of years ago, were talking about discovering supernovae, and they did it by blink comparing, clicking on a mouse on the computer screen. This is an old Zeiss blink comparator for photographic images. So just to conclude, there are many more telescopes, so if anybody has a chance to visit South Africa, try and make it to Cape Town and have a look at these things. There's lots more to see. And one other thing I was really surprised about is a number of the astronomers that I saw at the Star Party said you have to be sure and see the planetarium. Well, I generally avoid planetariums because I think they're kind of clunky. But this one has really super high resolution, laser generated display, and they can handle millions of objects in real time, motion without jaggies and things like that. So it's quite impressive. And in fact, that facility is used, on afternoons on the weekend for the general public, but in the mornings on weekdays, scientists use it for data visualization. Thanks a lot.
Thank you, Michael. You've got me wanting to go to South Africa now. All right, so we've got here at the museum, we've got Yuri's Night coming up on April 13th. I believe it's 7 p.m. to 11 p.m. There's free food, cash bar. There's going to be, I guess, what they call a science slam. So it's like a scientist competing, some cool presentations. Yeah, so apparently it's going to be pretty cool. You can come check it out. International Astronomy Day is coming up on April 21st. We're going to be set up here at the museum for solar observing from 10 to 4, and for an evening star party from 8:30 p.m. to 11. If you're interested in volunteering, please contact Chris Tarrant. Okay, and Chris, are we going to shuffle those a little bit? Sure. So we're just moving a little bit quickly. So I'm going to get John Thompson and Rick Wagner to come do their observations. And then we'll go to the break after that. Yes. So you can advance. So we've got nothing here. You can advance slides to the right.
There's just
Pointer
one.
on the.
Just one.
I think you've got a couple. Oh, wrong way. Are these in the right order, Chris? Chris, can you put us back on observations there?
I'll put it back.
Okay, 66.
You were advancing backwards. You gotta make sure you use the other button.
So the one on the
Okay.
right.
Back in February, I attended the Winter Star Party in Florida. Normally it's held in the Florida Keys, but this year, because of storm damage in the Keys, it was held at the Chiefland Astronomy Village, which is somewhat further north, about 7 degrees further north in latitude. This, of the 6 nights, we only had 1 or 2 good nights that the ground was rather damp and threw up a lot of fog. But this is the very last night, and taken with my panoramic camera. And you can see Orion there. And what I wanted to particularly point out was the zodiacal light, or zodiacal light, off to the right-hand side. That's what it is. It's reflection off micrometeorites that are populating the plane of the ecliptic, sort of the plane of the Earth's orbit. It's dust and unconsolidated particles, maybe fragments of asteroids as they're hitting each other, and it gets illuminated by sunlight. And it's best seen around the equinoxes in March and September. But you have to have very dark skies to see it. I've only seen it myself maybe 4 or 5 times that I can think of in my life. But then you can see also the Orion and the winter Milky Way sort of stretching from the lower left and then sort of arching over Orion. One picture of the Flame Nebula, and you can just barely see the horsehead. There's a little bit of trace of red nebulosity down below it. Even as I was taking those pictures, the haze was starting to come in and was starting to get a little bit of dew in the lens, so I didn't get as much contrast as I'd hoped, or in some pictures, other pictures that I've taken. That's M36. I thought it looked a little bit like a starfish. You can see I was using a telephoto lens here, and you can see a little bit of chromatic aberration. I think that's what the red circle around it. It's possible it's infrared also because I've got an extended red camera, which probably contributes to that. Orion Nebula. Again, I was just using a telephoto lens on a Ioptron star tracker. And M46 and M47 in Puppets. And then above 47, there's also an Ngc object. I forget the number of that one. But you can see a rather different morphology of those two clusters. One is primarily composed of fainter stars, which probably means it's an older cluster. It's also a little more dense. And then the other one, M47, is brighter stars, which tend to be younger, maybe red giants perhaps. And you can see that was also and right in the middle of the winter Milky Way. You can see that extended star background. I think this is the last one. The Rosette Nebula. That's up sort of off of, to the left of Betelgeuse and Orion, a few degrees over. And it's something that can be seen on telescopes, but it tends to be very faint. It's quite large. It's over half a degree. I forget exactly how big. But it's a nebulous cluster that's red hydrogen emission with the nebulosity and then the stars around it. I think that's not the last one.
Yep. Okay. Thanks, John. Okay, Rick. Here you are, sir.
Here is the right-hand button.
Yep.
All right. So a little bit of a retrospective. I've been collecting observations for a while, intending to come down and show them. And so back to December. Anybody remember December? It was a lot like it is outside today. We had the Geminid meteor shower, and I was out photographing for a few hours. You'll remember Paul Cloninger showed a whole bunch of images of his Geminid shots. And I actually came up with the idea that we would be able to coordinate. We can probably triangulate on some of the meteors, except that it turns out that all the time that I was observing, he wasn't, and all the time that he was, I wasn't. And so I think we're going to have to try and coordinate things a little better next time around. But one thing he did show you was a meteor train, and so this is about the best meteor that I caught. You can see the Pleiades down to the left there. And as I was going through these a couple of days later, it's hard to see, but there is a wisp of cloud there. So these are 60-second exposures, and you can see that over the following about 4 or 5 minutes, it didn't seem to move much, but it twisted a lot, which I thought was kind of interesting. This is about the best shot I got of multiple meteors. I had to keep switching cameras. I don't have a great wide swath of sky to work in from home. So I had to keep moving the camera, and every time I move the camera, of course, I can't keep adding the meteors in like some of the guys do. But what I did think was interesting is you get the effect of all the meteors coming out of some point back in the sky. So what I did was I took the 5 and I drew nice little orange lines, and you can see they really come out of a nice little point in the sky. So I was quite pleased with that. Back at the end of January, we had a lunar eclipse, partially visible in the dawn sky. My wife and I both trudged out into the middle of the lake at 6 o'clock in the morning to get a nice view. And unfortunately, this is about as far as we got before it moved into the cloud, and then it just got thicker and thicker. I tried a video, it didn't work out terribly well, unfortunately, either. So this is about the best shot I got. This is a picture of Alderaan. I was setting up one evening and had the scope out, set up in the parking area, and cameras cooling and everything, and I went back into the shop, and I'm looking at my computer, figuring out what am I going to actually observe tonight, and I noticed there was a really good ISS pass in about 10 minutes, and it was going to be going right past Alderaan, which is the southwest corner of Cepheus. So I just whipped outside and pointed the telescope at the star and started it taking 30-second exposures, and after about 5 minutes later, pow! And it went through the field of view. Now, my first thought, of course, was that, this thing is just like blindingly overexposed. But then I wondered, how wide is that band? So I measured it, and I measured it at 54 arc seconds wide. And it turns out that the solar panels, at the distance the space station was at that night, should have been 52 arc seconds wide. So what you're seeing there is the actual width of the space station going by. And that's a 400 millimeter focal length. So you can appreciate that in a telescope it would be very easy to see detail. The Boltwood 40 centimeter scope, I haven't got auto guiding on it yet, so if I'm doing pretty picture stuff, I'm limited to fairly short exposures. M1 was handy, so I decided to shoot it for a little while. So this is about 20 minutes of 30-second exposures. And then I decided I needed some color in it, so I put my 9 centimeter refractor with my RGB filters on, and did about another half hour, 45 minutes of color imaging, and then blew that up enormously so that it would fit, just to give me some color on the image. And while I had the 9 centimeter refractor out, I've got an extender on it, so it's operating at f9 now, which is kind of slow. But I thought it's giving me an 800 millimeter focal length, so I can maybe see something in all these stupid little teeny galaxies that are out in the spring skies. So this is M88 and M91. This one I thought was quite neat. It's a barred spiral, and then you can see the spiral arms. But what I thought is kind of neat is that the spiral arms don't seem to actually start on the ends of the bars, which I thought was always sort of de rigueur. So, and then there's a bunch of other small galaxies in the field of view. This is in the Coma Virgo group. Ngc 2403. This is a couple of hours. These ones are shot with Canon 60DA on the 9 centimeter refractor. And there are sort of 2 to 3 hour exposures total. And the Witch's Head, this is down just slightly west of Rigel. And it's one of the really appropriately named nebulae in the sky. And that's it. Thank you.
Okay, so we're going to go to the break now. Let's take a quick 5-minute break. So it's 8:20. Let's meet back at 8:25, and we'll resume with Dr. Lobel's presentation. Thank you. Okay, we're going to go back to observing reports. We're going to start with Gordon Webster. I am going to ask that everyone presenting their observing reports try to get through them as quickly as they can. We are running long today. Laser, advance slide.
Sorry?
Laser's the green button.
Green button and then advance, right?
Yep.
Okay. Good evening. I have 3 here for you. There we are. Okay, so in Astronauts and at the meetings, we've been introducing the challenge objects, and I actually managed to find the galaxy 3079. It's a large spiral galaxy about 50 million light years away. It's located in Ursa Major, and it's apparently, I couldn't see it, but probably a prominent bubble forming in the galaxy center. And this sketch was done with my 152 millimeter refractor at 76 magnification. Okay. The next one was the lunar challenge, which was the crater Cepheus, which is named for the same character as the constellation. And it's just on the next page. So it's a 40 by 40 diameter crater with steep terrace walls, and it's overlapped. It's the upper one here, up here. Okay, and it has an overlapping crater on the rim, and the crater below is Franklin. It's about 56 kilometers in diameter. And that was done with my 120 refractor at 200x. And last, I actually found another galaxy. It's 11.2 magnitude. It's about 46 million light years away, Ngc 3310. And that was with my 12-inch Dob at 300x. And there's actually a hint of spiral arms were visible. Thank you.
Thank you, Gordon. We've got Bob Wolfson next. That one advances, that's late.
Gotcha. I was interested in the challenge object also. Gordon called it Mink 1-7, and or M1-7, and my astronomy program called it MI 1-7. And you know that old game where you ask Google something and it doesn't know the answer? Well, you type that in and see what you get. It's more weapons than there are astronomical things. Anyway, there it is. As you can see, I didn't even know where it was. So if you kind of look at that area right there, and then we'll expand it a bit. It's a planetary nebula, and it actually has a PK number that I could have found a lot quicker. And it was Minkowski, if you do that. He made 4 lists. This is this first list and 7th object on the first list. And he was at Mount Wilson Observatory in Los Angeles. It must have been a really nice sky then. It certainly is now. And he was made these lists on Mount Wilson. All right, next thing. This time of the year, everybody knows where the Big Dipper is. It's standing up on end. This is looking east right about now. And there's 3 really spectacular galaxies there. And you really should get your scopes out, or just borrow a scope or go to a star party and see them. It's 51, 63, and 64. And they are spectacular. They all have names that associate with what they look like when you look at them. And we'll start at the bottom. That is a black eye galaxy. And when you see it in a telescope, it really looks like it has a black eye. And then we have the Sunflower Galaxy. I've never been able to see it as a Sunflower Galaxy, although I've seen some pictures of it where I think they overprocessed it. It kind of looked like a sunflower. There's more red in it than I've ever been able to see. And then the most, to me, this is actually one of the first things I ever looked at in the telescope. It's M51, the Whirlpool Galaxy, and in 1845, I think, some guy looked in a telescope and saw the spiral arms. It was the first time spiral structure had ever been seen by humans. Anyway, again, that's probably my favorite celestial object. Good luck trying to find them.
Thanks, Bob. All right, next we've got Taras. Is Taras here?
Thanks. There was a position of Mercury and Venus later, or rather first weeks of March, and I tried to take some pictures, but before I just take the screenshot to show you. Oops, I hit the wrong button. Where's the laser?
You advance with this one.
Mm-hmm. This is the laser?
That's the laser, yeah.
Oh, there you go. So the position, rather conjunction, happens when two planets align on the same line. So from the point of view on Earth, we can see these two. Oops.
Uh-oh. Here, let me get you back. All right.
Something happened.
Yeah, we went back a little bit.
Thank you. Sorry about that. So on March the 3rd and few following weeks, there was this orientation of planets with regard to Earth. We could see them nicely aligned, and shortly before sunset, we could see them together, which is the meaning of conjunction, right around the point where sun set. You can see though that they have different positions with regard to the sun. So the Venus is almost like behind the sun, while Mercury is on the sharp angle if looking from the Earth. So when I took pictures, it looked like this. Surprisingly, Mercury looks like a typical phase of Venus, which is a crescent, which explains the sharp angle. And Venus, almost full planet in a full phase. Now this is not a real distance, I just put them together for comparison to see the difference in their sizes, and I did my best to get as much details as possible, although there are none. But the challenge was because they were so low above the horizon that the air disturbances plus atmospheric dispersion made that practically impossible to see shapes at all. So this was a result of roughly 2,000 frames. This time manually went through and chose the best ones to stack them to get this crescent shape. And Venus has a little bit of, you can see that this side is a little bit dimmer because of the face. It was not ideal behind, right, like in front of the moon, otherwise you wouldn't see it, but it's waning phase. M81, it's, the three galaxies together, two of them, 81 and 82, they're prominently seen, and there is the third, which is Ngc Galaxy. So the only specific about this picture is I tried to use a modified camera to capture as much as possible of hydrogen alpha, but there was practically none. You can clearly see the spiral arms and some details like the dust lanes, but it didn't show up much of hydrogen and star formation regions. So apparently it is the case. This galaxy is one of the least known in terms of, well known in terms of stars not being born. So within all the observation cycle for that galaxy, there was only one record that there was a supernova in M81. And the reason for that, because those three galaxies are so close together, they form a local group, and all the hydrogen from M81 was shifted towards the center of gravity and later on acquired by M82. So instead, M82 has lots of star formation regions, lots of hydrogen in it, while M81 is not that prominent for it. Thank you. Oh, actually, I think there is one more.
There.
Yeah, one more, which is a picture of the moon taken the same night when I was imaging M81. It was just a nice seeing, and this is still about 10 pictures stacked and processed, but I was satisfied with the amount of details which I got, and I think it makes more or less a decent picture. Thank you.
Thanks, Tanas. We've got Jen Thompson next.
How do I not
Advance the slide on the right, laser with the green. Don't hit the back button.
Don't hit the back button. Okay, we should put tape over it or something. As you know, springtime is a good time to look at galaxies, when the sky permits, obviously. And one of the many galaxies that are near the Big Dipper is M108, and that's the large galaxy that we see in the middle of the frame here. So at the time, I was doing a live broadcast on Night Skies Network, and this is a 60-second exposure. I believe there's 20 frames stacked alive during the broadcast. And as we were looking around, we noticed that there are some other small smudges. If you look, there's a little smudge there, and then a little smudge here, a little smudge here. So we thought, well, there's actually a lot more galaxies in that image than are obvious. So after the broadcast, I dug out, it was Carte Ciel that I used, to actually figure out how many galaxies I did actually pick up in this image. And it ends up that I could actually see in my frame 57 galaxies.
Wow.
So where there's a number, that's the visual magnitude of the galaxy that was recorded in the image. And where there's another circle with no number, I didn't think that I actually picked it out in the image, but still, there's a lot of galaxies in there. So I thought that was pretty neat. And by far, the dimmest object I've ever observed from my backyard, this is just in Alta Vista area, downtown, is a 20.16 magnitude galaxy. So I thought that was pretty cool. Okay, thank you.
Thanks, Jim. Paul, you're next.
Thanks, Oscar. Well, I had several pages of notes prepared, but we'll leave those because, after all, my middle initial is E for expeditious. Running a little short of time. So. Anyway, Oscar put out an observing challenge. I'm glad you picked that up. We used to do that, and it's kind of a cool thing to see. So I took that to heart, and I tried to bag the images or the objects that Oscar put forth. So the first one was M44, the beehive cluster. So this is the beehive shot through a 70 millimeter APO with a Canon 60DA. It's an interesting cluster, one of the nearest open clusters to us here on Earth, about 600 light years away. Well, interestingly also, it's one of the first objects that Galileo observed with his telescope. So about 600 light years away, and contains about 1,000 gravitationally bound stars, most of which, about 2/3 of which, are small M-class stars. About 30% are more like the sun, and there's a smattering of very large stars. So interesting object to see, easy to see, don't need any visual aids at all. It's just it's a faint smudge to the right of Leo, and you can see it under a reasonably dark sky just with your naked eye. So M44. Next one I've got. This one I really rose to because this has been on my bucket list for a while. And I haven't finished with it yet, but Oscar mentioned the galaxy Ngc 3079, and so there's my image of it. You can see, is there a laser on this one?
Yeah, it's at the top right there.
That
the
one there?
green
Okay,
button.
thank you. You can see there's a smattering of other galaxies here, but that's the main one, and as Gordon pointed out, it's about 50 million light years away. It's got a very active galactic nucleus there with a supermassive black hole about the size of the one in our own galaxy. So that was the object itself that Oscar posed for us, but it happens to be nearby an object that, like I said, has been on my bucket list for a while, and I'm not done with this one yet. But I thought I'd take this on, and that's this guy here. Whoop, that guy there, sorry. Ah! Let's go back here. Here we go. So yeah, that's the twin quasar, and I'll try not to do that again. Up there, those two little eyes in the sky, they look like stars. This is, I have a penchant for very distant objects, and so as I say, this one's been on my bucket list. I want to do some really long duration deep imaging with my most sensitive camera, but because Oscar posed the challenge last month, I thought I'd see what I could do just with the 60 DA on my 11-inch. And that quasar it's a single galaxy, but it's about 2/3 of the way across the universe, about 8.7 billion light years away. And it's being gravitationally lensed by a cluster of galaxies that are about half that distance between us and the quasar itself. Those galaxies, actually, I'll zoom in on the next one there. Oops. Did a bit of a close-up there. There's the quasar itself. Actually, I'll light her up there. That's the guy there. You can see there's a couple of really faint little smudges there. These are not members of the cluster that's actually doing the gravitational lensing. To capture those galaxies, well, similar to the gravitationally lensed galaxies that I showed you about a year ago, you require a really deep exposure for those because they're very, very faint, and I have to throw my most sensitive camera on it. But regardless, there is one giant elliptical galaxy in almost between those two points of light that's doing most of the lensing. The other clusters the other galaxies in that cluster, of which that elliptical is a part, contribute to it as well. But it's doing the main imaging, and they're only separated by about 6 arc seconds. So, give you an idea, for those of you that have looked at planet Mars, for instance, through a telescope, that's about 1/4 of the diameter of Mars. So, as you see through your telescope, so very distant object. This is one of the first gravitationally lensed objects that was ever observed. It was predicted back in 1936 as a fact by Albert Einstein as a consequence of general relativity. But in a paper that he published in 1936, he put out this concept, but he said, yeah, there's no possible way we'll ever observe this. So, sorry, Al, I did this in my backyard. Anyway, so stay tuned. I'm going to, as I say, this is on my short list for deep imaging. I'm going to try to get more detail on this, plus the actual galaxies that are doing the lensing. The next one. Well, Oscar, could you have picked a more obscure, dimmer object? I mean, holy smokes! As we've already seen, this is barely distinguishable from a star in the background there. And I just bagged this last night, actually, through some trees, because I figured I had to get the third one to get the hat trick. So there it is there. It's a planetary nebula. It's tiny. I wasn't able to find a distance to it, but I'm thinking it's on the order of 10 to 15,000 light years away. It's similar to something like the dumbbell, but much smaller and therefore much farther away, because they're probably comparable in size. So a little Ngc guy there. There's a bit of a close-up on it. Planetary Nebula. So those are the three. Got the hat trick, Oscar. You're going to have to try harder. But I couldn't leave it at this, because I actually have been doing a lot of imaging up in the Gemini area as well. And so my last object image is not of the three challenge objects, obviously, but it's, oops, there it is there. Sorry, forgot my arrow. It's this guy. So this is the Cone Nebula. This is a fantastic. The whole region up there at the foot of Gemini and through Gemini is quite fantastic. That little planetary nebula is also in Gemini, but this is one I've wanted to capture for quite a while. This is a 3-hour exposure, and I actually did this as a mosaic with my 11-inch. So there's pretty high definition on this one, and stitched them together. The Cone Nebula itself is up here. This is an active star-forming region. There's stars forming inside the pillar and up near the head there. This is about 7 light years across, so it's about almost twice the distance from here to Alpha Centauri, just to give you an idea of the scale there. And as I say, this whole region, NGC 2264, if my memory serves, encompasses all of these objects. So here we have the Cone Nebula. This is the Christmas tree cluster. Okay, so if you can picture this as the apex of the Christmas tree, and this is the trunk. There's the stars that form the rest of the Christmas tree. This is the Phosphor Nebula down here. You can see these dark tendrils of gas coming up from and blotting out part of the view of this very central part here. So yeah, very, very rich region. Not easy to observe. Certainly the cluster of stars there are easy to observe, but yeah, the Cone Nebula is quite faint, required a lot of exposure just to bring it up. So that's my ending object. Thank you very much.
Thanks, Paul. Those are some fantastic images, and I want to be clear though that I don't take all of the blame for the obscurity of those objects. I'm pointing at you, Gordon. So I figured that I needed to stand up to the challenge I put forward as well. So I took the opportunity to image that Planetary Nebula. As you can see, it is tiny. I think Paul spoke to it at length, but in my field, it's just right there. When I was doing the image, I wasn't certain that I was in the field because I took my first couple of sub-exposures and all I saw was stars, so I re-slewed my telescope about 5 times to make sure I was in the right spot. All right, so time for the observing challenge for April. I think a lot of you guys were making sacrifices to those deities because we had that week-long stretch of clear skies, which we haven't had in years that I can remember. So just remember these important facts. For our beginner challenge, I'm hoping people can get out and look for M81. So it's a fairly bright object. Anyone with a modest-sized telescope should be able to pick that one up from the city. It's an Ursa Major, magnitude 6.9. For our intermediate challenge, we've got the Hickson Compact Galaxy Group 44. So the brightest, it's in Galaxy Group in Leo. NGC 3190 is the brightest at 12th magnitude, and the other 4 galaxies are just brighter than 13th magnitude, so see how many of those you can pick up. And for the adventurous crowd, we've got NGC 4284 at about 14th magnitude, near M40 and NGC 4290, also in Ursa Major. And our lunar challenge, Messier on the moon. So we're going to see if you can find Messier and Messier A. So I know I promised last month to get them on the website and I failed at that. But I will try my best to get them up on the website this month. And I'll also send them out to the members list so that everyone gets them.
And they'll be in Astronauts.
And they will be in Astronauts. Okay, Jim, you had a couple of things to say.
Thank you. I know I talked about this a little bit last month. I'm just here refreshing everybody's memory that Astronomy Day is coming. It's a couple of weeks away. There was already a bit of a discussion about the activities that will be happening here at the museum. If you want to get involved in that, you can contact Chris. If you want to get involved with the sidewalk astronomy that happens every year at Silver City near the Gloucester Center, you can contact me, and that's usually an all-day event. Set up in the morning to look at the sun and then transition to the moon and any planets that are up in the evening. It's always a good event, gets lots of exposure and people excited about astronomy and science in general. So it's a great activity. I really highly recommend people get involved. And the second notice is for the upcoming work group that we have. We had one last night. It was a great evening talking about double stars. I learned a lot about all of the interesting characters involved in it. The one coming up next month, about a month away, is hosted by Pierre Martin, who you may remember as the person who travels around the globe getting amazing shots of meteor showers. He's going to be presenting what he knows about meteors and how to observe them. So that's next month. Right, that's all. Thank you very much.
Thanks, Jim. So we've got the GA coming up. I think it's Canada Day long weekend in Calgary. As you know, we hosted last year's GA, and it was a fantastic success, and thank you to everyone that supported that. And I think it's time perhaps we can lend our support to Calgary as well for those that are able to. So if you go to rascga2018.ca, you can register for the GA. FLO Star Parties, it looks like the one on the 17th was a success, so that's great. We've got one coming up on April 14th. And these are for members only. The schedule for our public star parties was sent out to the list, I believe, and that'll be up on the website soon, and I'll have a slide for it at next month's meeting.
Oscar?
Yes?
Just one point of clarification. It's for RASC members, not FLO members.
Yes.
Apparently there was some confusion on that. So everybody here is welcome.
Yeah. So all our AC members are welcome to this, to the FLO Star Parties. Stell's pick of the month is Mars Making Contact. These are the folks that help the club operate. This is where you can catch the recordings of the meetings. Thank you for coming. We had an audience of 107 tonight. That's great. Post-meeting entertainment. We'll have a post-meeting meeting at Gracie's again. Next meeting is May 4th. We're going to have Chuck O'Dale with a presentation titled "Why We Learned to Love the Bolides Until It Was Too Late." Signed, the dinosaurs. We will also have Dr. Robin Fiore presenting on auroras, the dark side of the aurora, how space weather affects technology. So these are some of the benefits of membership. You get the TED Bean Loan Library. You can borrow astronomical equipment. The Stanwatt Library, you can get some books and access to the FLO, as well as various publications. So if you enjoyed this and you're not a member of our club, please consider joining.